morning, good afternoon, and good evening. Thank you for joining us today. My name is Brent Berenson, and I'll be the moderator for our presentation. I'm the director of Fluor's Office of Technology, which focuses on using science, innovative engineering technology to build a better world. Our engineers, designers, and experts, our people, are the core of our success. As with other webinars, this will be a technical presentation. Today's webinar will be about advanced process modeling and the many ways in which process design relies on physical properties. Our experts will discuss some of the studies to highlight the importance of the best property method, especially when used in combination with other expert knowledge. The webinar will also highlight DIPPR as the premier source of critically evaluated thermophysical property data and correlations. With us today is Samantha Nicholson. Samantha is a Fluor Fellow in Process Simulation with expertise in gas plant and NGL fractionation. She considers her particular skills to be conceptualizing, predicting high-level process engineering outcomes, and understanding interdependence with processing facilities. These abilities work hand in hand with process simulation to be able to provide peer reviews and quickly understand simulation results and rationalize impacts for the client. As a working mom, Samantha is pretty busy at home. Her family includes a husband, 2 children, 1 kitten, and about 60,000 honeybees. Also with us today is Paul Mathias. Paul is a Fluor Senior Fellow with expertise in vapor-liquid equilibrium prediction, thermodynamics, and process simulation and CO2 capture. Paul is a chemical engineer with about 41 years of broad experience and an expert in applied thermodynamics and process modeling. He started his career on the ASPEN project at MIT, which developed the forerunner for ASPEN Plus. He worked at ASPEN Technology before joining Fluor in 2005. Paul has chaired sessions at the American Institute of Chemical Engineers and other technical meetings and was selected as the AICHE Fellow in 2015. He also chaired the DIPPR 801 project from 2016 to 2020 and is currently serving as past chair for the DIPPR Management Board with the new DIPPR leadership structure. Paul has 6 patents, over 90 publications, and has given over 130 technical presentations. In his free time, Paul enjoys listening to podcasts, typically during his daily walks, and he likes to write short books, especially catering to his grandchildren. Fluor has a very strong safety-driven culture, and as such, it is customary for us to start our meetings with a brief safety topic. Paul, would you please unmute your line to share the safety topic with us?
Thank you very much, Brent. This safety topic highlights the mitigation of a serious safety issue and also the benefit of bringing together a diversity of skills to solve a problem. HTHA, or high-temperature hydrogen attack, is a dangerous condition that can occur in process equipment constructed with steel and exposed to hydrogen at elevated temperatures and high hydrogen partial pressures. The picture shown here on the left is an example of a crack caused by HTHA. This is a very serious corrosion problem that can lead to faulty and unsafe plant operation. The API recommended practice 941, also known simply as API 641 curves, provide an authoritative guide for safe material choice to mitigate the occurrence of HTHA by relating material selection to hydrogen partial pressures and system temperature. Many of you will know these charts as the Nelson curves, named after George Nelson, who first introduced them over 60 years ago in 1959. Many industries, including petrochemicals, refineries, biofuels, minerals, and many others, have very good awareness of the risk of HTHA caused by gas and multi-phase mixtures. However, there is less experience with totally liquid or liquid-filled systems. We as Fluor experts improved estimation methods to use these API 941 curves for liquid-filled systems by bringing together the expertise of materials experts as well as process engineers. And we feel that this is a significant improvement in safety practice and technology related to mitigating HTHA. We will provide more details on this analysis in case study 5 of this webinar. Next, Samantha will provide an overview of this webinar. Over to you, Samantha.
Thank you, Paul. Many processing plants rely on simulation models to provide the thermodynamic properties for design, and thus the use of the correct starting blocks is critical. The selection of suitable thermodynamic property model is to predict the vapor-liquid equilibrium for system components is important and can affect simulation results considerably. Without attention to detail, chemical engineers can find themselves relying on powerful process simulation programs without having the proper background knowledge in applied phase equilibrium thermodynamics. Sometimes, poor choice in the selection of a property model is made, or even sometimes no choice is made at all and the default is used. Paul and I will talk about the benefits of special attention to property methods. Manipulation of these models in conjunction with other expert knowledge from the design team can improve safety and system design, cut costs for the client. So we'll introduce what property methods are and why they're important. We'll talk about some different property methods and what they're used for. We'll also remind the community about the American Institute of Chemical Engineers DIPPR database. We'll talk about Fluor's secured databases, which have been developed to better reflect actual operating data. And we'll also take a look at some case studies where a number of our specialists have been involved to improve design in terms of product purity, safety, and operability. Property methods are used to accurately develop the physical properties which we use for system design. This table shows some of the numerous property methods which can be used to develop a design. I'm sure most chemical engineers will spot some of the ones they're familiar with. I'm not going to discuss all of them now, but perhaps you will see that a lot of thought is needed to go into which property method is used. Process engineers should have a good feel for the property method to be used and how they evaluate their accuracy. You'll see here listed equation of state models, where an equation of state is a thermodynamic expression that relates pressure, temperature, and volume. Hybrid models consider liquid and vapor separately, often using an activity coefficient for the liquid with an equation of state for the gas. Some are considered legacy models, but continue to be used in specific applications where operating experience has shown good approximation to specific operating ranges. Often these legacy models have been incorporated into other models more recently. For instance, Kent Eisenberg has been incorporated into Sauer, Suave, Redlich Kwong, and Sauer, Peng, Robinson. Legacy models can still be relevant, particularly when making additions to an existing plant or using additional trains. Grayson Street was used on a recent Giga project after study work and discussion with our client. So we've seen that there is a great abundance of property methods. Each method has specific applications, and process engineers need to be careful to review simulator documentation to ensure that the correct property package is used for their application. Factors for consideration include the nature of the mixture, for instance, whether it's ionic or not. What's the mixture composition? What are the operating conditions? And is there parameter data available? Process simulators have a large number of methods available which are sufficient for most applications. Thermodynamic properties are defined as characteristic features of a system capable of specifying the system's state. The items in the table frame the properties of a component, and those properties are not dependent on the physical quantity of the substance. Each property method has a different approach to thermodynamics, for example, representation of the K value. Specific property methods have been developed to better model specific component mixtures. All of this is very important. There are, however, regular inaccuracies in simulated properties, which sometimes have poor matches to actual data. What do we do then? We rely on other methods to approximate systems. We're going to concentrate on this today because Fluor has the expertise to create new property methods to better match specific actual data. How does Fluor create new property methods to improve the match to actual data? One way is by modifying existing property methods. Using secured property databases helps us to do this. Secured property databases are ways of enabling improvement to existing simulators, property packages, based on operating data or literature data analysis. The data is available for specific or all members of the owner's organization for use in creating simulations. The database is not available to people outside the owner's organization, but making manipulation to the property methods in specific instances where there is a poor representation to actual data, this enables us to have improved process design. Fluor has a number of secured property databases to improve commercial simulator models. They benefit clients by ensuring improved system modeling, ensuring that their plants are designed fit for purpose. Fluor secure databases include the Fluor solvent process, which is used for gas purification for the bulk removal of CO2, Fluor Econosolve process, based on dimethyl ethers of polyethylene glycol for selective removal of H2S and bulk removal of CO2. C3 splitter for improved modelling of the separation of propane and propylene. Methanol, using a methanol-based solvent for removal of H2S and CO2. Ammonia water. The properties of aqueous ammonia are very important to many process technologies. FOSAM, which is using phosphoric acid to separate ammonia from acid gases such as H2S and CO2. This has enabled the development of a Fluor patent for removal of ammonia from Klaus feed gas, and there are lots of other ones as well. So on to DIPPR. Another tool which chemical engineers at Fluor have available is the American Institute of Chemical Engineers, DIPPR. The Design Institute for Physical Properties, DIPPR, is a technical society of the AICHE's. DIPPR's Project 801 database is recognised as the world's premier source of critically evaluated thermophysical properties. It is an extensive database of rigorously evaluated pure component data. Due to the cross-spectrum industry review and the data research and analysis techniques, DIPPR is considered to be the gold standard. It uses 34 constant properties and 15 temperature-dependent properties for compounds of interest. There are more than 2,300 compounds developed in the sponsor database. People who use DIPPR are often companies involved in manipulating chemicals in new products and manufacturing processes, and the database is based on industrially important chemical compounds. Each year, members are invited to vote for the addition of new compounds or the review of existing compounds to ensure the database is kept current by incorporating feedback. Correlations are developed by principal investigators and reviewed by industry experts. Fluor's been a member for more than 30 years, and Paul and others have chaired the membership committee during this period. The following are some quotes on how industry experts and our Fluor colleagues use DIPPR. With modern simulators, there's a tendency for blind automation, that is, not having the ability to see whether data and output are good or bad. DIPPR provides background data for checks and verification. It also provides additional data for some items which simulators rarely provide, such as auto-ignition temperatures and flashpoints. It's useful for streams where it's not possible to create an entire simulation, but details are needed for relief calculations, for instance. So, for instance, triglycerides and fatty acids, which are important in the process industry with the increasing prevalence of biofuels. That's as much as we need to say, that it's an important tool which Fluor has been working with for many years. We're now going to talk through a selection of case studies which show how, by our deep understanding of chemical thermodynamics, our chemical engineers work with other company experts to provide safe and operable designs. We have 5 case studies which will address, firstly, modification to property methods making to create a chemical model for vinyl acetate monomer production. Secondly, some of the ways we have improved our CO2 capture modelling. Thirdly, C3 splitter modelling in conjunction with our distillation expert Henry Kister. Third, the care required in reviewing thermodynamic data and transport properties using methanol, water, heat transfer fluid modelling as an example. More detail on high temperature hydrogen attack as touched on in the safety moment, where company senior fellows Paul Mathias, Gary Jacobs and Cathay Shargay provided their expertise. Case study 1 is regarding the chemical model for vinyl acetate monomer production. We were provided with a heat and material balance from a licensed technology. Fluor needed to develop a simulation to reflect this. Preparing the simulation, it became apparent that the property method did not reflect the license or technology or operating data. Fluor needed to better model the data and provide missing thermophysical property data. This allowed fully specifying equipment data sheets, two-phase and other hydraulic calculations, relief calculations and flare system hydraulics, and off-design upset scenario cases, calculations, for instance, based on HAZOP study requirements. So what did Fluor need to do? Thermophysical properties were required to simulate the VAM monomer production reaction. Areas which required particular attention were high pressure vapor phase reaction, CO2 removal, product purification and byproduct removal, heavy ends removal. After review of the data and the literature, 2 property models were modified for better representation of the data. These were molecular, which was used for most of the process, and electrolytic systems. This is a summary of the ASPEN Plus model modifications which were carried out. VLLE data was regressed using the ASPEN Plus data regression system, using various reliable data sources. For the first item on the table, about the adapted property methods, which was standard NRTL to describe the non-ideality in the liquid phase with Redlich-Kwong in the vapor phase. In this instance, the Redlich-Kwong method was modified to treat the acetic acid as a dimerizing component. Dimerization is 2 molecules of similar chemical composition coming together to form a single compound known as a dimer. In this instance, due to the carboxylic group and the position of the hydrogen bonds, gaseous acetic acid can form cyclic dimers with strong hydrogen bonds. This needs to be taken into account in design, but is not otherwise modelled by simulation packages. The second property method on the table is a subset of the first using the module's perturbation method and could be used for sensitivity checks. And the third is the electrolytic NRTL in the liquid phase, which was applied to CO2 removal, again with variations of Redlich-Kwong in the vapor phase. This was to model hot carbonate for CO2 removal. The result of the simulations were compared to the literature for completeness. Here's an example of the phase behaviour for 2 ternary systems, vinyl acetate, acetic acid and water. Points on the graph are actual data and the lines are calculated by the model. I think you'll agree that the calculated data matches the actual data pretty well. So why was the property method manipulation so important? Described previously that the expected outcomes for design, what the expected outcomes for design were, but in particular it should be noted that the data for the flash gas compressor from the licensor data was only being preliminary data. Design was firmed up using the property method to understand the extent of dissolved gas in the VAM streams, which in turn was integral to the machine package design. Also, in the long term, the client wished to develop training simulation, meaning a full plant simulation would be invaluable. Now going to hand over to Paul, who's going to talk about case study 2, which is the optimization of process design for CO2 capture.
Thanks very much, Samantha. I'll now, as Samantha said, move on to talk about CO2 capture technology. The transition to net zero will certainly not happen overnight, and sequestration and capture of CO2 are expected to provide a useful technology to mitigate climate change in the medium term. Fluor has been developing and offering CO2 capture technology for more than 2 decades. Process modeling is particularly critical for CO2 capture processes due to the large energy requirements and capital costs. Just to give you an example, post-combustion CO2 capture could reduce the thermal efficiency of a power plant by something like 20%. By contrast, CO2 removal from natural gas, the reduction in thermal efficiency is an order of magnitude less, or about 2%. Hence, accurate and reliable modeling is of vital importance to minimize TIC, or total installed costs, and also operating costs. Samantha mentioned the value of secured property databases for process technology. Fluor has developed these databases for its technology known as Economine FG+. This technology has been validated for several CO2 sources, including those from power plants, cement production, and SMR, or steam methane reforming. Significant effort has been devoted to ensuring a technological advantage for Fluor's technology, both within the company and also in collaboration with partners. As an example of working with partners, Fluor is collaborating with PNNL, or Pacific Northwest National Lab in Richland, Washington, to develop a slate of water-lean solvents. It's another example of the advantage of bringing together a diversity of skills to facilitate technology development. Fluor, as you may know, has expertise in process modeling, process design, plant construction, and operation and cost estimation, while PNNL expertise includes areas like molecular modeling, compound synthesis, a variety of sophisticated analytical techniques, and generally in chemical R&D. A leading candidate for CO2 capture solvent resulted from R&D by PNNL and its partners, and it's called PNNL, and it's shown here on the bottom right. Organic chemists call it N2-ethoxyethyl 3-morpholino-propane 1-amine. Given that long name, you can understand why simple chemical engineers like me prefer to call it EEMPA. This solvent has been tested in several lab and pilot scale evaluations and will soon be tested at the National Carbon Capture Center in Wilsonville, Alabama. Commercialization is certainly not far away. Fluor also has expertise in uncertainty modeling, about which we will say more in this presentation. Fluor CO2 capture technology, Economine FG+, has been developed and validated by several pilot plant and demonstration plant studies. Pilot plant studies from Sulzer and Coke-Glitch help validate the property models and fine-tune rate-based absorption parameters, for example, the effective backing area. Extensive data from the demonstration plant together with E.ON at Wilhelmshaven, Germany, were further used to verify several advancements in Fluor's Economine FG+ technology, and also provided data to fine-tune the process models. These studies have made us confident in the vital importance of our modeling technology. I'll move on now to talk about uncertainty analysis. Process modeling is invariably the basis for quantitative design and analysis of chemical processes, especially CO2 capture. However, we need to understand the model uncertainties and how they impact the process design and plant operation. Some of the factors questions that we need to ask are, how good are the underlying data and models? Where are they weak and where are they strong? Which data are most important to develop reliable models? How accurate should the data be, and how large should the design margins be? An uncertainty analysis is certainly an effective way to quantitatively answer these questions. We have adopted a practical approach to uncertainty analysis by paying attention to the following points. Firstly, we need to ensure that the models meet asymptotic limits. That is, for example, as the kinetics gets very large, the model should be able to predict equilibrium. Secondly, we want to devise practical schemes to perturb calculated properties. And it's also important that the perturbations are based upon data analysis. And here again is some of the things that Samantha mentioned, and that is we pay very careful attention to the data and constantly are monitoring how well the correlations agree with the data. We've published an example of our uncertainty analysis in the International Journal of Greenhouse Gas Control, and in this case we have used AMP, or 2-methyl 2-amino 1-propanol, as the solvent. Details of this study are presented in this paper, and we won't go into many details here. My co-author is my colleague, John Gilmartin, who's a CO2 capture expert, and some of the key details are shown in the following slides. This slide presents some examples of the useful information that can be obtained from uncertainty analysis. The two graphs show the effects of uncertainties in two key properties of the model: VLE, or vapor-liquid equilibrium, in the chart on the left, and chemical kinetics in the chart on the right. And both charts show the effect of these uncertainties on two important process parameters: heat rate, which is the specific steam consumption in the process, that is the amount of steam consumed, or BTUs robbed from the pilot plant per pound or kilogram of CO2 captured, and the solvent rate, which is related to pumping costs and also column flooding. Referring to the chart on the left, the green arrow indicates that if the VLE, or more specifically the CO2 K value or the CO2 partial pressure, which is kind of equivalent, is actually 20% higher than the model prediction, the heat rate will rise by about 9%, and the solvent rate will rise by about 25%. And this gives us an indication of the model uncertainties and also the specific impact of the uncertainty of VLE. Similarly, moving to the chart on the right, the green arrow indicates that if the kinetics for a key reaction, in this particular case, the carbamate formation reaction, which is a key reaction in capturing CO2 or dissolving it, is actually a factor of 3 lower than the model prediction, the heat rate will rise by about 12%, and the solvent rate will rise by about 22%. It's results like these, together with our process understanding, that have enabled Fluor to estimate the overall design margins. Next, Samantha will talk about improved modeling for one of our heat transfer processes.
Thank you very much, Paul. Case study 3 concerns improved modelling of C3 splitters. C3 splitters separate propane and propylene by distillation. The separation is very difficult to simulate accurately, as the propylene-propane relative volatility is close to 1, typically 1.05 or 1.1. Small errors in the relative volatility cause large uncertainties in column design, for example, for the reflux ratio and reboiler duty. A property database was the property database of the best available data was developed by Fluor in collaboration with the recognized industry distillation expert and Fluor Senior Fellow, Henry Kister. Paul will be blushing at the moment, but as Fluor Senior Fellow, his and Henry's exceptional level expertise were used for the creation and validation of this database and property model. This is one of the secured property databases I mentioned earlier, which you will remember is limited to the use by Fluor, and it enables the best design for C3 splitting processes. We've tried to demonstrate the particular difficulties with propane-propylene splitting on the graphs here. Uncertainty analysis can be also applied in this instance, thinking about the C3 splitter. The left-hand graph is the bottom end of the splitter, where the propane product is produced, and it actually isn't too difficult separation, because the difference in relative volatility is 1.27. The range of reboiler duties on the graph is plus or minus 3% over the range of the graphs, you'll notice. It's the top that actually is of more concern, since the relative volatility is about 1.1. So the graphs we have here show how sensitive the process is. One thing to note is that there is an additional consideration, which is the required purity of the product. Looking at the curve on the graph on the right, if you are making chemical grade propylene, which is something like 5% propane in propylene, the sensitivity isn't too bad. This is the double red line. So if you then change the relative volatility for about 1%, which is a typical uncertainty, then you make a 2% difference in the reboiler duty. On the other hand, if you make polymer grade propylene, which could be 1%, less than 1%, which is the dotted red line, or sometimes it could be even 0.5% propane in propylene, you see the sensitivity is much greater. So looking at the dotted red line, for 1% propane in propylene, then a 1% uncertainty will be getting up towards 12% change in reboiler duty. That shows that we need to understand our processes and apply realistic uncertainties to design. Case study 4 is a quick reminder that care is required in reviewing thermodynamic data and transport properties. The example here is methanol water heat transfer fluid modelling. So it isn't only thermodynamic properties which should be considered, it's also very important to remember the transport properties. Methanol plus water is a binary mixture used in heat transfer fluids. The liquid viscosity of the mixture can be significantly higher than that of the pure fluid viscosities depending on operating conditions. In this instance, an accurate fluid viscosity model was developed by fitting the available property data. This in-house knowledge can be applied to develop property methods for other non-ideal fluid mixtures. So these graphs of methanol water concentration versus viscosity. This is interesting when you notice the scale for the viscosity. The graph on the left goes from 0 to 3.5, but the right-hand graph goes from 0.1 to 100 on a log scale. As expected, the viscosity varies with weight fraction and also with temperature. But what is surprising is the viscosity changes so much for the mixture compared to the pure component at low temperature. At 20 degrees, there's a range of viscosity of about 1 centipoise and 1.75 for 50% methanol and 0.5 for pure methanol. Without manipulation, the property package would have predicted about 0.74 centipoise for 50% methanol for a matter of interest. For minus 60, however, pure water is obviously frozen, but 50% methanol, the viscosity is more than 60 centipoise compared to 3 for pure methanol. Without special attention, the simulator would predict 5.4 for 50% methanol, which is a factor of 11 out. I doubt any commercial simulator would give you the degree of accuracy that this independent modelling has provided. As I said previously, this is an example of the benefits of being able to model a system correctly when there are unexpected values for transport properties. the method employed can be used for other examples. As a reminder, if you have any questions, you're welcome to submit them on the Q&A tab and address them to all panelists. So now it's over to Paul, who will give more details about the case studies he touched on earlier during the safety moment.
Thanks very much, Samantha. As I stated in the safety topic, HTHA, or high temperature hydrogen attack, it's a dangerous condition that can occur in process equipment constructed of steel and exposed to hydrogen at elevated temperatures and high hydrogen partial pressures. The API curves provide an authoritative guide for safe material choice to mitigate the occurrence of HTHA by relating material selection to temperature and hydrogen partial pressures. These curves use the result of experimental tests and actual data acquired from operating plants to continuously update practical operating limits for carbon and alloy steels in hydrogen service. As I mentioned earlier, HTHA can and does occur in liquid filled systems, and hence the use of the API curves requires estimation of the hydrogen partial pressure as a function of temperature, pressure, and liquid composition. However, there is less experience in applying the API 941 curves to liquid filled systems. My colleagues Gary Jacobs, Kathleen Chargay, and I published a paper this year in Chemical Engineering Progress that helps material science and process engineers estimate hydrogen partial pressure in liquid mixtures so that the API 941 curves can be applied. We will next provide the takeaway messages and results from this paper, but we urge the readers to actually read the paper for the details. The chart on the left is a qualitative representation of API 941 curves. The actual curves offered by API have pressures up to 13,000 psi or 90 megapascals and temperatures up to 1500 degrees F or 816 degrees C. Note that the API 941 curves have a negative slope, and this means that the ability of a particular steel to withstand HTHA diminishes as the pressure increases. Also, more corrosion-resistant steels are required as the temperature increases. I should inform you that material experts typically apply a safety margin of 50 degrees F or 28 Celsius to account for uncertainties, for example, in temperature or hydrogen partial pressure. And just as an example, I'm going to show you some specific results for the steel grade required at a hydrogen partial pressure of 500 psi or 3.4 megapascals. Carbon with no PWHT or post-weld heat treatment, which is the dashed purple curve at the bottom, will work up to about 410 degrees F or 210 degrees C. If we now add post-weld heat treatment, we move to the red curve, and the resistance temperature moves up from 410 to 470 degrees F or 243 degrees C. If indeed the system has higher pressures, then we may need to move to alloyed steels. And as an example, we show you what the green curve would give us, which is 1.35 chromium and 0.5 molybdenum steel. This actually gives you pretty good resistance. It can go up to 890 or 477 degrees C. We want to caution you that this is just a cursory view of these, and experienced material experts really should be consulted for reliable material recommendations. This slide shows some specific examples of process equipment where HTHA may occur. The desulfurization column shown has hydrogen injection upstream of the reboiler, and that's the top right hand of the figure, and hydrogen recycled to the reboiler, which is the middle left of the figure. And there are several places where there may be risk for HTHA. The gas lines, for which we have more experience, are shown in red, but I want to focus on the liquid lines that are in blue. Just to bring to your attention, the bottom of the chart, looking at the blue curve at the bottom of the chart, upstream of the pump, the hydrogen partial pressure, of course, is the same as the vapor partial pressure at the bottom of the column, since that is in equilibrium. But after the pump, it becomes more complicated and HTHA partial pressure estimation techniques are needed. And this is the reason why accurate estimation of the hydrogen partial pressure in liquids is so important. And I next want to show you the methodology we came up with to do the estimation. The chart on the left illustrates the approach we've taken. Point B is actually in the single phase region, right? And so which we don't really have a hydrogen partial pressure. So there are two ways in which we can artificially create a vapor. By lowering the temperature, that's number one, to point C, or by adding hydrogen at fixed pressure to reach point D. And what we have done is propose 5 methods to calculate the hydrogen partial pressure by using the properties at point C or point D to estimate the hydrogen partial pressure at point B, which of course is of interest. The details are presented in our paper and are very briefly described in the caption in the graph on the right. We think that method 3 is the most accurate, but methods 4 and 5 are acceptable alternatives. And particularly want to point out that method 5 is useful since it does not require the commercial simulator to report fugacities, and these are not available in some process simulators. The graph on the right compares the hydrogen partial pressures predicted by the 5 methods as a function of pressure. The boiling point is the point going all the way to the left, which is 650 psia. And at this point, all the methods agree because there is indeed a vapor phase for which the partial pressure can be directly calculated. The predictions from methods 3, 4, and 5 are approximately equal. Method 1 indicates that the hydrogen partial pressure is invariant with pressure, with total pressure, which of course, as you may recognize, is not correct since it ignores the so-called pointing correction. Method 2 estimates a hydrogen partial pressure that is biased way too high. So we recommend methods 3, 4, and 5 and have actually used these in some Fluor studies. This concludes the presentation of our case studies, and I will now move forward to a summary of our webinar. So let's move forward to the summary. So how does Fluor actually acquire useful operating data? As Samantha mentioned in case study 1, vinyl acetate monomer, we checked the model against the design provided by the vendor. In some cases, we modified the model. In other cases, we challenged the design. This is an iterative process since we constantly go back to the data and our experience. In case study 2, which is CO2 capture, we demonstrated the use of lab and pilot plant data to improve our models. And in case study 3, which is Fluor's C3 splitter model, I worked with distillation expert Henry Kister to use data from operating columns to help to fine-tune the property models. Let's move on next to talk about this whole question of intuition and understanding. Having a human analyze, question, and interpret results is absolutely critical. Experienced process engineers can tell when the results in the model don't seem quite right or quite normal. The discussion on DIPPR shared this observation of an expert who said, with the DIPPR database, I can tell when my data is coming from and how accurate the data are rather than being simply given tabulated numbers, which I'm asked to blindly accept. With the increase in automation, it's doubly important that engineers obtain a good feel for properties. Case study 4, the viscosity of methanol water, presented by Samantha, really highlighted the importance of recognizing that some properties may be different, may be unexpected, but they're also correct because they come from empirical data which has been validated. We also need to improve our intuition. The discussions on property uncertainty analysis highlighted its use in developing design margins, but also its use in developing a feel for the effects of various uncertainties, as Samantha pointed out when we talked about uncertainties for the C3 splitter. We at Fluor work very hard to make the best property models available to our engineers. In case study 1, we made sure the property model modeled the vapor phase dimerization of acetic acid. And the discussion on secure property databases highlighted the value of providing our engineers with the best and most current property methods. Of course, this is an ongoing effort. Finally, in conclusion, that I want to tell you that Fluor has strong expertise in applied thermodynamics and indeed other process technologies, and this ultimately ensures safe and operable designs. Thank you very much for your attention. We now look forward to receiving your comments and your questions. Thank you again.
Thank you, Paul. Let's take a moment to address the questions that have come in through the chat. And again, as a reminder, you can submit your questions to the Q&A and please address them to all panelists. First question will go to Paul. It is sometimes necessary to use more than one thermodynamic model in a process. How do you decide when it is necessary, and can it cause inaccuracies in the simulation?
Yes, there are certainly areas where we sort of have to switch a model. And for example, one area is sort of what Samantha mentioned in the VAM, or vinyl acetate monomer process, where we may use a hot carbonate to capture the CO2, whereas we use some sort of a modified NRTL model for the rest of it. What you typically do is worry about the switch point, and typically what you can either keep the temperatures and pressures the same and sort of throw away it, or ignore a little bit of enthalpy difference and so on. Oftentimes you really have to make sure where you're doing that, and there is some experience in doing that, but the best, of course, would be to have a single model, but oftentimes we don't really describe nature well enough with a single model. But that is an ongoing effort, and hopefully over time the correlations will improve, and certainly folks around the globe, experts around the globe, are working on this.
Thank you, Paul. Another question for you. For the CO2 capture example, was it an equilibrium-based model or a rate-based model? If rate-based,
sorry, actually, it is a rate-based model. We have extensive use in the use of rate-based technology to describe it. In particular, this one was a model. Fluor's technology is based on economy and FG plus. Some of our technology hasn't really been described completely because it's proprietary. But I would refer you to the work that we did in collaboration with PNNL and other groups such as RTI on the EEMPA solvent, because that has actually been published extensively and in fact has been tested extensively. As I mentioned, there are lab tests that have been done. There was work done at PNNL labs. There's also work done at RTI in North Carolina. And as I mentioned, this solvent will soon be tested. This is an ongoing effort at the National Carbon Capture Center in Wilsonville, Alabama. So I believe it's absolutely necessary to use rate-based model for chemical absorption. And I think that I would not get any disagreement from experts in the field.
And just as an extension to that question, where does diffusivity fall in the order of important properties as shown on slide 27?
Well, it's somewhere in there. I think it's less important because we typically get a very high enhancement from the chemical kinetics, and oftentimes it's sort of mixed up in there, which is why I think even after we put in the best physics that we can, we've got to recognize that some of these models don't capture everything, and that's why we do pilot plant studies to sort of do the final fine-tuning. I sort of mentioned this, but in a lot of these models there's something called the interfacial area factor that we may adjust, and these are adjusted based upon either lab data or pilot plant data. I wish our models were better. I think our models are pretty good and they're improving all the time, but we do have to put in empirical factors, and that's really why the experimental measurements are so critically important in order to validate the technology and make sure that we can actually scale up equipment. I think we as a sort of a global community are getting better at this, and we certainly can get better, but ultimately it's some sort of a combination between good, practical, rigorous process modeling and the experimental data. There's constant complementarity, I think, between the two.
All right, thank you for that. Next question is for Samantha. Do you think design margins, tray efficiencies will come down as we improve understanding of properties and uncertainties in simulations, or will owners want to stick with established norms?
Well, I could think of an example where on the C3 splitter, where we looked more deeply into the licensor design. It was an established licensor who'd done a lot of C3 splitter work before, but using the calculations that and the methodology that we previously described, we came up with about a 5% difference between the reboiler duty that the database correlations gave and what the licensor gave. So we looked at uncertainty analysis, and I couldn't overcome this 5%. So speaking to the licensor, it became obvious it was a design margin. So in this instance, the uncertainty analysis allowed interrogation of the design margins and allowed the client to get the actual margin that they really wanted. So we need to ensure that the client gets what they want, really. They may want some additional design margin. They may want to design the plant to exactly do what it says on the on the nameplate, but there's a discussion there with the client always. So sometimes, for instance, we can cut down design margins and save money. Other times we might want to think about the future. The client might want to debottleneck in the future, and they might be thinking about that when they do the original design. They might say, well, yeah, at the moment we want to do such and such, but in the future we can see that we want to be able to do more. So absolutely, it's best to know what you're dealing with and where the design margins are. You might be able to cut down and save money, or you may want to keep that, but it's all discussion with the client.
Thank you, Samantha. The next question goes to Paul. For the methanol water mixture, is the cubic plus association CPA method a good alternative according to your experience?
Well, but my experience with that method is mostly from the literature, and I know it to be a very good method. I've got to admit, and I don't know how much that method has been applied to viscosities. I've seen a lot of application to phase equilibrium, vapor-liquid equilibrium, and liquid-liquid equilibrium, but I don't know whether it has been applied to viscosity. I'll have to look into it, and maybe we will research this subject and get back in the official Q&A answers we provide soon.
Okay, thank you. The next question also goes to you, Paul. Will machine learning eventually make equation of state, activity-based property models, etc., redundant?
I think that's an open question. If we actually just read the popular press these days, I mean, there are such advancements made in machine learning and artificial intelligence that I don't think we should be saying no. But my own feeling is, from all my years of experience, is that if we can sort of identify and define a problem, in this particular case, we have fairly good semi-empirical or phenomenological methods, and we know how to improve them based upon data. And then these models are thermodynamically consistent, and they do phase boundaries correctly, because those come from, for example, flash calculations or distillation calculations. Given all of that, I don't quite see it. I think at the present time, it may be better to look to applying these methods to something like properties we don't know very well. What is the color? How long will a compressor last? When should we be doing preventive maintenance? But again, I think we should all be cautious about predicting the future. So there are a lot of people working on this, and I know that improvements are going to come. The simulator vendors have been pushing a lot of AI technology. But I think currently, if I look at it, I can see that the need for improvement in the technologies that Samantha and I described really as lab studies and pilot plant studies and improvements in approximately existing methods. And the previous questioner talked about the CPA method. Yeah, that's certainly a very good method, and that brings in a lot more fundamentals to the prediction. There are also SAFT methods, but these are not AI methods. These are what, in some sense, are traditional methods that are going back to what we know, like intermolecular interactions, and going from there to build up a model. But again, I know that there are people out there trying to bring in new AI, so I urge them to continue trying. And ultimately, we as ones who develop designs and troubleshoot, we want to use the best technology available, and we will when AI becomes competitive.
Okay, thank you. Next question, also I'll direct to you, Paul. Could SAFT models from statistical mechanics eventually replace the cubic equations of state?
Oh, yes, absolutely. I think that there are a lot of people working on SAFT, and I think that there are conferences that are held regularly. But currently, the problem I see with SAFT, and maybe this is a personal opinion, is that there are just too many flavors of it, and it's very hard to get a single one that I can apply. But again, it's like the CPA model that I mentioned earlier. These models certainly have better underlying fundamentals than a cubic equation of state. And so it may just be a factor of time before these models get better. And there is a lot of research being done around the world to improve models. So again, I'll repeat what I said about AI, and that is we as industrial experts should be open to using the best technology available to solve our problems. And going back to this slide, Samantha mentioned that sometimes we go back to Grayson Street. That's what, 60 years old. It still may work. At other times we use others. So I think we sort of have a suite of tools available to us, and we pick the best one to solve our problem. And we certainly should be open to new models appearing on the horizon, and we'll adopt them as soon as they show that they are an improvement.
Excellent, thank you. And it looks like that is all the time we have for questions. I just want to thank you again, Samantha and Paul, for this informative webinar and the time you spent today in the preparation. And thank you to our audience for attending today. It's been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on fluor.com or following our social media channel using #InnovationBuilders. If you'd like to send us your email notification, if you'd like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention and thank you again for dialing in today. We will send out a compiled list of the Q&As within a few days, along with a notification that the webinar recording is available for replay on fluor.com. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back to you. From all of us on the Innovation Builders team, have a safe day.